like to welcome everybody to the Complex Human Data Hub seminar, and we'll also welcome our speaker today, Nathan Evans. Nathan is a PhD from University of Newcastle, and so there are a few of us there that were around when Nathan was doing his PhD. And since then, he's been well travelled. He's spent time at Vanderbilt and also in Amsterdam, but he's now on a DECRA at the University of Queensland. And Nathan's going to be talking to us today about reaction time modelling and modelling and basically the identification of psychological processes. So take it away, Nathan.
Cool. All right, let's hope this works. I want present. Oh, do I want presenter view? I don't know. God damn it.
Probably,
let's go play from start and then, oh, sorry, I shouldn't start swearing.
Share your screen.
Yeah, I want
we are recording, Nathan.
No problem, it'll be fine. All right, so then I should go that. Is that working good?
Yep, that's all good.
Fantastic. So I went for a quite provocative title, if you didn't notice, The Death of Accumulator Models. I'm going to move you over there. Oh, you don't want to move over there. There we go. Got rid of it. All right. So you'll understand what I mean from that very soon, hopefully. But very quick. Oh, how do I go next slide? Oh, damn. That's a bad start.
Might be space or click.
There we go. It's click. I clicked every button except for click. All right. So I'm very, very, very quickly going to go through evidence accumulation models for those who don't know them already. Hopefully you do, though. I'll assume most people will. And so the idea of evidence accumulation models is, can people see my mouse?
Yes.
Good. People can see my mouse. That will help. So the general idea is that people, this idea is that decision-making is composed of people accumulating evidence from the environment until they reach a threshold which triggers a decision, right? So here I'm going to show you the basic diffusion process lots of people use. The idea here is that you're accumulating evidence in a relative sense. So it's option 1 versus option 2, and it accumulates at some rate called a drift rate towards a decision alternative. You've got some starting amount of evidence, and then once it hits a threshold, you make a decision for that response alternative. And there's also some time dedicated to non-decision times. Essentially, you've got 4 key parameters. You've got the drift rate, which is theoretically how good you are at the task. The starting point, which is your initial bias, but I won't really be talking about that. The threshold, which is your caution, and the non-decision time, so sensory encoding and motor responses, there's kind of everything else. Now, I'll define some terms as I'll use in the talk. You may have different definitions, but this is just to clarify what things are going to look like in my talk. So I define evidence accumulation models as models that take this kind of general form, that they attempt to explain RT distributions via this evidence accumulation account, that you accumulate 4 alternatives until you hit a threshold and then make a decision. I define diffusion models as those with relative evidence. So the ones that you just saw before, where you're accumulating for option 1 versus option 2. You don't have an absolute amount of evidence for each option. You're accumulating based on the relative evidence for each option. And then I have what I call accumulator models, which I may be pronouncing dead in this talk. I don't know. I do know, but I don't want to spoil it. And so these are the evidence accumulation models with with absolute evidence. So you've got the LBA, the LCA, the walled model, racing walled, so on and so forth. And so for those who don't know what I mean by absolute evidence, here's a very quick look at the LBA. There's a lot of noise on this slide, so don't look at it. But the main point is that you've got these 2 separate accumulators, right? You've got accumulator for response A and accumulator for response B, and they're accumulating separately, right? Until one hits a threshold and a decision is made. Okay, so evidence accumulation models have been successful for a long time, right? I think there's little doubting that. They're older than me, and if age is any indicator of success, that means they've been successful, and they're even older than both of my parents. So these things have been around for a long time and been very successful for a long time, right? They explain data well, they've answered lots of interesting questions, they've certainly been a success. However, recent research has begun to question the validity of some of these models. And this has been mostly regarding this thing called selective influence tests, which I'll go through the logic of. So this idea of selective influence tests is that you want to use an experimental manipulation that you think is valid to test whether the model is valid in that it matches what you think the manipulation should do. So as an example, the logic kind of is first you have to be able to implement it, right? So if you can implement experimental manipulation at X, and then you think manipulation X affects construct Y, then you can have a selective influence test of parameter Z if it's supposed to measure construct Y. So if you think that manipulation X affects construct Y and parameter Z of model 1 is supposed to measure construct Y, then you can then assume that if model 1 is valid, then manipulation X should only affect parameter Z. If they're both if they're both influenced by construct Y, or they both influence construct Y, however you want to put it, there should be this selective influence, right? Where this manipulation that affects construct Y should also only affect parameter Z that maps onto construct Y. However, this logic of selective influence tests is really dependent on how valid this manipulation is, right? If manipulation X doesn't actually only if manipulation X affects construct Y, but also other constructs, or doesn't affect construct Y, then you're going to not have a valid selective influence test. And so just to foreshadow a bit, this isn't mainly on selective influence tests, but this kind of builds into the identifiability issues that I talk about. So an example of a selective influence test could be like a difficulty or a coherence manipulation, right? So you've got a random dot motion task here and 3 different coherences, right? You've got what is a very easy coherence, a kind of middle coherence, and an incomprehensible coherence, right? And the idea is that this coherence should affect how difficult the task is, which drift rate maps onto, and therefore it could be a selective influence test of the drift rate parameter. Now, kind of the key recent study of selective influence has been this Dutil et al. Study. And so sorry, I just need to keep an eye on the time. Okay, 13. And it essentially looked at a whole bunch of different selective influence manipulations. I think it's arguable how selective these manipulations were, and how the models, how correct the models were in identifying these manipulations. And so this is also based on some previous work from Voss et al. And Ray et al., which also looked at experimental manipulations and how they influence the parameters of these evidence accumulation models. And so this is like, when you read through this paper and try and look for figures to glue in, there are no good figures that simply express the results. It's actually god-awful. But this is kind of the best I think I can do for the time being in the talk. Anyway, the key thing you want to think about are these 2 things in this plot, right? Blue is misses, so there was a manipulation and it didn't, and that parameter wasn't affected. And orange is false alarms, so there wasn't a manipulation, but the model said that parameter was affected. And as you can see, there's quite a bit of orange and blue, and there was a lot of debate amongst people in the study, but this kind of led the main authors to the study to conclude, hey, there's a problem with the models. They're not correctly passing these selective influence tests. The second plot, which is also very noisy, but hopefully we'll get some of the point across that I'm trying to make here, is that they also looked at the correlation between approaches. And so each bubble is the correlation between teams, but the key thing to kind of look at here is that you've got groups that did simple diffusion, groups that did full diffusion, and groups that did LBA. And I think the most important thing here is to look at the main correlations to the point I'm going to make, and that is that the LBA correlated inferences with the LBA correlated quite poorly with inferences with the diffusion model. Much more poorly, at least, than other groups used the same model did, and other groups that used the full, much more poorly in the simple correlated with other groups that use the simple, and the full with other groups that use the full, and simple and full. LBA correlated the worst with them. And so I performed a study, which is a preprint now, to kind of look at both One, what's the go with the selective influence manipulation, specifically the speed accuracy instructions one, which I'll explain briefly. And two, what's the go with these different conclusions between models? And so in this paper, I don't know how to go back, so there's no going back. But in this Think Fast paper, so I looked at the simple and full diffusion model. I used 6 data sets with SAT instructions. So these SAT instructions are supposed to manipulate the speed accuracy trade-off. Essentially, you tell people either to be speedy in these blocks, so to kind of ignore errors and just kind of go as fast as you can without guessing, or to be very accurate, so to try and get everything right if possible. And that's kind of your manipulation, and it's assumed that that should only manipulate threshold as threshold relates to caution, and these instructions should only manipulate caution. Bayesian model comparison and participant level analysis for generalizability, not super important points though. And so these plots, all my plots are just so, there's just so much info on them, so I'll explain it in the detail that I think is necessary, right? So here on the left, we've got the diffusion model analysis. I think that should be everyone's left. And we've got 3 columns here. We've got drift rate, threshold, non-decision time. And then we've got 6 different studies on the rows. Not super important right now what studies they were, I think. Red indicates a decreasing effect, blue indicates no change, and green indicates an increasing effect. Now the increase is from accuracy to speed. So for example, red with drift rate means that drift rate decreased from accuracy to speed, which is kind of the, well, I'm going to common findings. But it's one of the violations that people often see. And so, for example, in this Dutil 2013 study, the result here is essentially that, well, drift rate seems to decrease when you put people under speed emphasis. So does threshold, and non-decision time's kind of on the fence. Not super strong if it is.
Sorry, can I ask a question?
Yeah, sure, go for it.
It's Christina here. Hi, Nathan. Sorry, can you just talk briefly about what these experiments involve people doing apart from speed accuracy? Like, what's the stimulus, and are they the same in all of these? Sorry, I think I missed it. I'm really sorry.
No problem. I didn't say that. That was my bad. So they differed between studies. So I think Dutil 2013 was a random dot motion task, so was 2019. Evans 2017 was a brightness discrimination. Lercher 2017, I always pronounce her last name wrong though, which is really bad, was a fig rule task. It's a more complicated, longer response time task. Ray et al. Was another brightness discrimination, and Wagenmakers was a lexical decision task.
Okay,
So
and is it okay to compare these ones generally because they're all doing the same sorts of things, or?
So for me, the key thing here is that we want to know, I guess, generally, what do speed accuracy instructions do, right?
Right, irrespective of the experimental paradigm. Yeah.
Exactly. That's
all I need to know. Thanks.
Oh,
sorry.
No problem. I should mention that that's my perspective, at least. People may very well have different perspectives on maybe speed accuracy trade-off instructions do different things based on, based on the experimental paradigm. But for me, I think it should be general. But anyway, the key kind of finding here with diffusion seems to be, apart from this Dutil 2017 data set, which doesn't really seem to have a decrease in non-decision time, all the others seem to show decent evidence for a decrease in non-decision time, all except for Ray's a bit weird because it's got a bit less. But there's fairly strong evidence for a decrease in threshold, which there should be, and less so for drift rate, except for a couple of studies, 2017 and 2013 and 2014, Dutil and Ray. And so in general, it seems like the main conclusions of the diffusion model is that threshold decreases and non-decision time decreases, and drift rate does sometimes. So potentially this study, but not across all studies, right? Whereas the LBA, you seem to have a very different results, right? First of all, the most striking difference for me is that you don't see very consistent evidence for a decrease in threshold across speed accuracy instructions, right? I mean, for me, it seems like speed accuracy instructions could influence other things, but I feel like they should at least influence threshold, right? Which is what the diffusion model is showing, but the LBA is not. it's showing that a lot of the time people aren't decreasing their threshold with speed accuracy instructions. And unlike the diffusion model as well, you see that people are almost never decreasing in non-decision time. But you do get what seems to be in several studies, bigger decreases in drift rate, or more evidence for decreases in drift rate. So for me, these, although it's in no way consistent across every person, every study, there does seem to be somewhat striking differences to me in the conclusions of the diffusion and the LBA. And so for me, there's two kind of takeaway messages from this, right? There do appear to be selective influence violations, but I am hesitant to say there's an issue with the models, because I just don't think instructing people is always going to do what you think it's going to do, right? I think if you instruct people to be more faster at the task, they could just start pressing buttons fast. You know, they could try and motor respond as quick as possible, right? If you instruct people to be more speedy, they could get nervous about doing the task and feel under pressure and therefore perform the task worse. So I don't think failings of this specific selective influence manipulation is a failing of the model. I think it's perhaps more a failing of the manipulation, and it not being a valid manipulation. But I guess the even more key finding for me was that these patterns of violations really differ between models. In the diffusion model, you have clear threshold effects, but also a fairly clear violation in non-decision time. Whereas in the LBA, you don't have clear threshold effects, and you have a fairly clear violation in the drift rate. In some studies, it was more inconsistent in the LBA. So what's kind of the go here? I mean, this seems strange given that I've kind of grown up on this logic of it doesn't matter what model you use; they all tell you the same thing. You know, it's irrelevant. So I guess one of my main questions here was, well, what's kind of the go, right? Why are we getting different conclusions between these models when many people in the past have very clearly tried to say, you know, you get the same conclusions about psychological processes. So this kind of leads to the bulk of the talk, right? Which is the identifiability of response time models and, you know, trying to make sure they are reasonably constrained to have good measurement properties. So this preprint, same model, different conclusions, is about the identifiability issues within the LBA. And so what I did here was I used LBA and simple diffusion model assessments. You could obviously use the full diffusion model, but across this I've used the simple diffusion model because it has, there's less ambiguity in the measurement properties of the simple diffusion model. Everyone agrees the simple diffusion model has good measurement properties. This is not the case for the full diffusion model. So you've got the LBA and the simple diffusion model. Large scale parameter recovery, I used 8,000 parameter sets generated from a hypercube with scatterplot and correlation assessments. And it's the same kind of design as Dutil et al., right? So you have a single factor and two conditions, and 1,000 trials per condition, and you see what varies between conditions. So does drift rate vary? Does non-decision time vary? Does threshold vary? And the same, of course, with my previous SAT assessment. And so what you get is an interesting pattern of results, right? So these are the scatter plots, generated values on the X, estimated values on the Y. Each point is a different data set. It's quite messy, and I should probably add something like density to make it clearer. And then correlations using Pearson's up in red, right? And what you see is that something like what you see is that I call this V-diff because you have different drift rates for the two accumulators in absolute models, in what I call accumulator models. And so I call V mean the kind of overall drift rate, the average drift rate between the two accumulators, and V diff the difference in the accumulators. And V diff is approximately what the drift rate is in the diffusion model. As in the diffusion model, you've got the relative evidence. And so what you see is with V diff, the recovery is excellent, right? You've got a correlation of 0.99. Everything falls quite neatly along the red line, which is the line of perfect recovery. And there isn't too much spread. Whereas threshold effects, which is B, threshold is B, are very bad. You get a very low correlation, 0.63. And although it's generally around the line of perfect recovery, you get this huge variation, right? To the point where you're almost just looking at a square or a rectangle, right? If you generate with a value, a threshold difference between conditions of near -1, you can estimate anywhere up to positive 0.5. Same if you generate around 0, you can estimate anywhere essentially from +1 to -1. You practically can't identify differences in threshold with the standard LBA when you're looking at differences between conditions. And then non-decision time is somewhere in the middle. I mean, I think it's still reasonably good, but it definitely could be better, right? So you get a correlation of 0.91 and you get still a reasonable amount of variability, right? So if you generate with a value of 0, you can still get between positive 0.1 and negative 0.1, which for me is quite a bit, but I think it's a lot better than what you're seeing, this rectangular or square shape almost you're seeing for threshold. However, the diffusion model is essentially the golden child the simple diffusion model, I should say, is essentially the golden child gold standards, you know, of what we want to see of recovery, right? We get essentially excellent VDIF recovery, so the drift rated diffusion model. We get excellent threshold recovery and excellent non-decision time recovery, right? The variability in essentially every case, I guess VDIFs, the drift rate's debatable. Being the other two cases, variability is much lower, and you can clearly identify the differences, at least to me, across conditions. So the kind of general conclusions of the study is the simple diffusion model seems to provide excellent recovery for these differences between conditions. We can use the diffusion model to measure if we have two experimental conditions, what parameters differ between them. But the LBA, not so much. The drift rate, or the VDIF, whatever you want to call it, the drift rate difference is good. And the non-decision time's okay, but threshold is extremely bad to the point where you practically can't identify changes in it, right? You have no way of knowing whether the generating value was an extremely low negative number, an extreme negative number, an extreme positive number, or 0. This, however, does explain some of the previous results that we saw and that I showed. In the sense that this would explain in my SAT paper, the Think Fast one, why the LBA didn't really show threshold effects, right? Of course, if the threshold parameter is unidentifiable, the Bayesian framework, not to go too far into this, is going to push it towards 0, right? Because making it non-zero doesn't really add anything. And so this explains why I wasn't really getting threshold effects in many participants in my big SAT assessment, right? Because it seems like these differences in threshold aren't really identifiable, and therefore it's just going to push them towards being null effects based on the prior. So then the further question from this, and now this is moving from actual submitted preprints to mostly in prep studies, is how far does this issue go? Is this just a weird LBA is bad and the devil thing? Or is this a more general issue across response time models? So one immediate question is, does model selection fix things? So lots of people don't actually use parameter estimation approaches where they try and estimate the difference. They instead try and use model selection approaches where they define a model where the parameter doesn't vary across conditions and compare it to a model where it does vary across conditions. And then rather than trying to estimate what the difference between conditions is, they just try and figure out, is there a difference between conditions or not? So one question is, does model selection fix things then? And so this is kind of the ideal plot, and this is what we see for the difference in drift rate difference between conditions. So VDIF difference between conditions. So here on the x-axis, we've got the generating VDIF difference. And then here we've got the difference in log marginal likelihood between the complex model and the null model. Essentially, this is the log Bayes factor and can can be interpreted as anything below 0, so below this red line, is evidence for the null, and anything above this red line is evidence for the alternate, the complex model where the parameter does differ between conditions. Now, this is just looking at the VDiff difference. So the null model is VDiff is constant across conditions, and the alternate is VDiff differs across conditions. And this is kind of the ideal plot that we want to see if a parameter is, if the model recovery is successful, right, on a large scale. What we want to see is that when the generating value is close to 0, we get evidence for the null. And as we spread away from generating values of 0, we're more likely to see evidence for the alternate, that it's non-null, until it gets extremely high in the tails, right? So this is kind of ideally what we want to see, and this is what we see for differences in VDiff. Now, do we see this for thresholds? The answer is very strongly no. It doesn't matter what when we are generating with more extreme values of threshold differences, we are more likely to see higher evidence for the alternate, right? But generally, it's very plausible, even in extreme negative and extreme positive generating values of threshold, to observe evidence for the null. And there's not this clear U-shaped pattern that you'd want to see, right? There's a clear recovery problem here, right? Where it's very difficult to see, it's very difficult, how do I put this? The model selection approach doesn't fix things, right? And I think that's actually the point of the next slide. Yeah, the model selection approach doesn't fix things, right? If your parameter is unidentifiable and you try and use nested model comparison by seeing is it 0 or is it not, it's going to have the same issues as just trying to estimate the parameter. There seems, to put it more concisely perhaps, there seems to be a clear relationship between parameter recovery and nested model recovery. So using model selection is not a get out of jail free card when your parameters are unidentifiable. I should mention that this is only for nested model recovery. This doesn't mean non-nested models will have an issue. So if, for example, you were to compare the LBA to the diffusion model, you still could get good model recovery here, right? It's about this nested model issue and seeing, do parameters vary across conditions? Okay, so the second kind of talking point here is, what about other accumulator models? So is this just an LBA thing, or does this apply to other accumulator models that we know about? As I talked about before, the LBA, the LCA, and the racing walls. And so here we have the same results as before. It's the LBA, VDiff is good, non-decision time's all right, threshold is extremely bad. And then I've called the racing walls the RDM for the racing diffusion model, just to clarify this. But the pattern of recovery looks fairly similar in the racing diffusion model. So VDiff is again excellent, and non-decision time is again all right. Now, threshold is a bit better, I'd say, but this is quite subjective, but it still has the same issue, right? It doesn't matter whether when you're generating with a value of 0, you could really observe anywhere from -1 to +1 difference, right? You don't really seem to be able to identify these changes in threshold in the racing diffusion model. The same goes for the LCA. The LCA is a bit worse on vmean, which I'm not really talking about, so I won't get into that. But it's quite similar on VDiff and non-decision time, but again, you get the same issue in the LCA, right? You get these differences in threshold that aren't identifiable. And so this seems to be a general issue across these accumulator models, right? With the level of constraint that they're commonly implemented with, where you just estimate these two different drift rates, you just can't identify changes in threshold, which is very important, and lots of people have tried to do in the past. So what about single accumulator models? Now, when I say single accumulator models, you have paradigms like the detection response task. There are probably others, but they're not coming to mind right now. Things where you don't require a choice, you just have to press a button when you see a stimulus, essentially detection tasks. And now people have used models for this, right? I think it's Ratcliffe and Van Dong in 2011. They modeled the DRT and PNAS, and there's been lots of DRT is detection response task. There's been lots of DRT modeling since then, right? And so these use the single accumulator model, where rather than having racing accumulators, you just have one accumulator that goes, and when it hits the threshold, a response is made. So if we use a single accumulator variant of the LBA, then we again see a similar issue. Again, you can't really separate it. I mean, I feel like I'm just repeating myself here, right? But the issue is fairly constant, right? Again, if you generate with 0, you could estimate anywhere between 1 and -1. Same with, sorry, I should mention that in all cases, the racing diffusion model, the racing world seems to be slightly less bad, but this is subjective than the LBA. But again, the same issue, right? Now, this is the model that's often being used to analyze DRT data in the past, right? The single racing, it's not racing diffusion anymore, right? The walled model, right? And you can't identify these differences between conditions and thresholds. And same if you were to use a single LCA, so that means just essentially a leaky accumulator, you again get these issues in identifying thresholds. And so it seems no matter which of these absolute evidence accumulation framework models you're using, no matter which of these accumulator, as I define the models that you're using, you keep getting this issue. It's a pervasive problem for accumulator models. It's not just an LBA thing. There is an issue in this framework that makes differences between conditions and threshold unidentifiable, something that people have very commonly in the past attempted to measure and attempted to assess. And so although the issue quantitatively differs, so you get higher correlations for the racing diffusion model than the LBA, the qualitative issue of you can't really separate big, if you generate with a 0 value of threshold, you can't really separate it from high positive and high negative values. So to get to the question that titled this talk, is this the death of accumulator models? I personally don't think so. Maybe you disagree, that's perfectly fine. However, I think it should be the death of unconstrained applications of accumulator models, of just essentially throwing parameters at the wall and seeing what sticks. This is a much less catchy title, so I didn't go with it, but I hope this is kind of getting across the general message of, I don't think this general class of models should be gotten rid of or die. But I think what we need to do is think more carefully about how we apply these models and the constraints we put on. So for me, the answer is constraint, as you probably guessed. And so while it's nice to allow this kind of maximal flexibility, just throw parameters at things and put minimum constraints on the model from a measurement perspective, it can often destroy the measurement properties of the model, right? However, constraint fixes the issue, which is great, right? So the fix I'm going to do is, I talked about before what I called V-mean, the overall drift rate across accumulators, which for me personally, others would disagree, but in my opinion, it's just theoretically uninteresting and meaningless in most cases. So what happens if we fix this value across accumulators over conditions? So V-mean is no longer allowed to vary in the model across conditions. So this is the previous LBA. As you recall, threshold is bad. I've really drummed this home. And here's the one with fixed V-mean. And as you can see, things get substantially better. VDIF actually seems to get a bit worse, which is interesting. I don't exactly understand why, but it's on the quantitative side rather than the qualitative side, right? You can clearly you can clearly know whether the generating value was 0 or not, right? Non-decision time gets much better. The correlation goes way up to 0.98, and there's a lot less variability. Although it's not easy to tell because of the different scaling on the figures, I probably should have made them the same scaling. This gets much better. And threshold gets substantially better. You still get some issues in the tails where you get some underestimation and I guess you get an overestimation of the absolute magnitude of the differences with extreme generating values, but you can much more clearly separate 0 effects from non-zero effects, right? And this is the case, I'll go through this more quickly, but this is the case for all of these models, right? All of these accumulator models. So in all cases, the non-decision time and threshold identifiability is much better. You can now more clearly identify these changes and thresholds across conditions. And it didn't cost you an arm and a leg. You didn't have to throw away these modeling frameworks. All you had to do was fix v-mean across conditions. All you had to do was not allow the maximal model and throw essentially as much flexibility as you could. So increasing the constraint on models seems to mostly solve the issue. I mean, the correlations weren't perfect, the scatter plots weren't perfect, the variation wasn't zero, it didn't look as good as the simple diffusion model for the most part, but it seems to mostly solve the general qualitative issue of threshold differences being unidentifiable. How much time I got? Still a bit. And so to me, this shows that we have to put more time into understanding the measurement properties of our models. I feel like we often feel like that because these models are based on theories, we get a free pass, right? We don't have to consider the measurement properties of things that more statistical, psychometrically inclined people would, right? But if we're going to use these models of measurement tools, then I think we really have to more strongly consider the measurement properties of the models and what constraints are necessary to ensure that they're robust and that we're not getting, we essentially don't have unidentifiable parameter changes. So as a quick note, a very quick note, I'm sure this will start a fight, but as a very quick note, it isn't only accumulator models that have problems. If you drastically increase the flexibility of a diffusion model, you'll also get issues. There'll be different issues, but you'll get issues. So one example is collapsing thresholds models. So I showed you before, you've got a fixed threshold. So no matter how long you've been making the decision for, you always need the same amount of evidence to make a decision. Well, collapsing thresholds kind of buck this trend and go, well, over time you need less and less evidence. This can either be nicely curved like it is here, or a linear decrease, a straight line. And so over time with collapsing thresholds, you need less evidence to make a decision. And if you use a linear decrease, so the collapse is just a straight line, then the identifiability of the parameters of the diffusion model, drift rate, thresholds, and this slope, the slope of the collapse, stay fairly well identified. But as soon as you bring in what's called a Weibull collapse, which is the one I showed you before, just then, where it's curvy, which has a shape and a scale, the measurement properties go to hell, right? You can't estimate threshold anymore. You can't estimate the shape of the collapse. Well, very slightly. It's more complex than I want to go into. And you can't at all estimate the scale, right? So by adding these collapsing thresholds, you drastically increase the flexibility of the diffusion model and give it problematic measurement properties too. Same with the time-varying diffusion models, so time-varying drift rate models, such as the Smith and Lilburn one, right? So they use a time-varying drift rate where you start with essentially zero, it's a scaling factor, right, on the drift rate parameter. So essentially you start with a scaling factor of 0 and over time it increases until it reaches 1, which is the maximum scaling factor. And this was their what I think is a neat instantiation of a time-varying drift rate. However, it has problematic implications for measurement properties of the diffusion model. So if you use just their base model without any different conditions, then it's essentially completely unidentifiable, but this is also because it's essentially mathematically unidentifiable because they added an extra source of noise and only fixed one of them, so there's the scaling issue in the model. And then even if you look at differences over conditions, which fixes the mathematical unidentifiability, you still get you can kind of identify differences in you can kind of identify differences in threshold and non-decision time, but you can't identify differences in drift rate. You can't identify the parameters that relate to the time varying process. As I said, it's a very neat addition, and I think it's a very nice way to incorporate time varying drift rates, but you've just got to be careful when using it as a measurement model, right? Because adding these very complex and flexible things can negatively affect the measurement properties of the model. And so a quick 5-minute wrap up, I guess. Why are we in this mess? So it's time for like finger pointing, and I was hoping to just find a way to point the finger at Adam and blame him for all of the world's issues, but I couldn't, unfortunately. So instead, I'll come up with some real issues. And so in my opinion, there's 2 issues to blame here, right? People don't do parameter recovery enough. They don't assess the measurement properties of the model enough. And when they do assess the measurement properties of the model, they'll often do this thing called data-informed parameter recovery. Now, data-informed parameter recovery is this idea where you take the model, you estimate the parameters from data, and then you use these estimated parameters that you took from the data as generating parameters for the model, and use that to generate data which you do a recovery on. So you estimate the model on data, you take the estimated parameters and use it to generate data, and then you estimate the model back onto that data to see if it can correctly estimate the data generating parameters which were based on real data. So what's my issue? Why am I bagging on data-informed recovery? What's wrong with me? In my opinion, recovery studies aim to test the robustness of our results by assessing whether the results we observe are the only ones possible. So essentially, formally, if we observe X, then the generating process is Y. Only one generating process could have resulted in our observations. So if we estimate a value of 1, then the generating value has to have been 1. However, by performing data-informed recovery, we actually do something else. We instead test what results our estimates could have generated. So formally, this would be if the data generating process is Y, Y being what we estimated from the data, then we observe X. So if we generate with a value of 1, then we estimate a value of 1. In my opinion, this isn't good, right? In data-informed recovery, we're testing one statement, which is the second statement, and we're inferring the converse. We're trying to infer if we observe X, then the generating process is Y, which technically this is the formal logical fallacy of affirming the consequent, right? We're not testing what we actually want to test. We're not testing the logical statement we want to test. We're instead testing its consequent and then trying to, we're trying to affirm it by testing its consequent. Now, perhaps you disagree, and I think many people do and will. Perhaps you're yelling on mute, Nathan, stop trying to tell me what I want to test. I'm sure people are. Perhaps you only want to look at parameters estimated from the data as they're realistic. However, I think there's a problem with this approach. I'll tell this through an example, which it's a toy basic token example, but I think it makes the point quite neat. Let's say I have a terrible measurement model. The model always estimates parameter A equals 1. Now I give it some data. The model estimates parameter equals 1. How shocking. Now to test the measurement properties of the model, I do a data-informed recovery. I generate data using the model and the parameters estimated from the data where A is equal to 1, as it always estimates 1. Then when I estimate the model on this data they generated, it estimates the parameter equals 1. So I generated with 1 and I estimated 1, therefore the model has perfect measurement properties. But this is clearly not the case, right? The model had terrible measurement properties. It always estimated A equals 1. The issue is that if you perform data-informed recovery, your recovery is influenced by the biases in the measurement properties of the model. If the model, the parameters you're estimating are only realistic if the measurement properties of the model are good. The parameters that you estimate are only as realistic as the model is good. If the model is bad, then your parameter estimates won't be realistic. They'll be biased based on the poor measurement properties of the model. So by only using these parameters, only using data-informed recovery, you can trick yourself into thinking the measurement properties are good when they're actually very bad, when they're terrible, right? So here's a pictorial example, but I don't have much time, so I won't go into it. It just makes the same point as before. Essentially a whole, I won't go into it. You can come back to this later in the YouTube video, though, if you want to have a look at it. So the take-home messages, I think, in this talk are under constraint's a real problem for evidence accumulation models. This isn't just a theoretical problem. I tested what I think are at least realistic situations. Then I have some new simulations with even more realistic simulations where the problem still holds. So it's under constraint's a real problem for evidence accumulation models. And the big offenders are what I call these accumulator models. The LBA, the LCA, the racing diffusion model. It seems odds coming from someone who trained in an LBA lab, but the diffusion model gets essentially a free pass in this talk. The accumulator models are the big offenders. So I think we need to be more vigilant of these issues by, one, ensuring that we constrain our models, that we just don't let everything vary over conditions and see what changes. This full measurement kind of perspective seems attractive in theory, but it just doesn't work with the models that we have, at least these accumulator models. And we also have to be more vigilant by assessing the measurement properties with data uninformed parameter recovery, not just taking the parameters that we estimate from the data, but looking at the full parameter space and seeing whether we can successfully recover the generating parameters, seeing whether we can identify the true generating parameters, seeing whether the measurement properties of our model are good enough. And I think if we do what I think are these fairly simple additional things, then we'll have a much more robust we'll have a much more robust field that makes much better inferences about empirical data. So that's it. So questions? Stop share.
Awesome. Thanks, Nathan. I think that one, that ought to generate some discussion would be my guess.
Yes. I'm also happy to stay into lunch if people want to talk further, but that's up to you guys.
So I have a more specific question, but I'll let others go first.
I've got a question, Nathan, if you don't mind. So I was wondering, why do you think the LBA performs more poorly at parameter recovery than even the racing diffusion model does?
So this is a good question. I think some of the issue is, you know Gabe's paper, the Tillman, Van Zandt, Logan one? Now, he shows in this that there's different levels of constraint with non-decision time in these different models, right? So the diffusion model is very highly, non-decision time is very highly constrained in the diffusion model, right? It's essentially constrained by the leading edge. Non-decision time is less constrained in the racing diffusion model. It's constrained a bit by the leading edge, but there's a bit more wiggle room. In the LBA, non-decision time is essentially unconstrained. At least by the leading edge. You can have a leading edge of like 0.4 seconds and estimate a non-decision time of 0. It's just the non-decision time is not well constrained in the LBA, right? So I think the issue is that non-decision time is also getting in on this trade-off. And you're seeing, so perhaps constraining non-decision time would also help out, right? And so I think non-decision time is getting in on this trade-off and making things worse in the LBA, but it can't make it quite as bad in the racing diffusion model because the racing diffusion model is more constrained by the non-decision time in the racing diffusion model is more constrained by the leading edge. Does that make sense?
Sure.
Nathan, Philip Smith here.
Oh, yeah.
How or to what degree are your conclusions about parameter identifiability dependent on the structure and the complexity of the experimental design, the simulated data that you're using to recover them?
This is a great point. So if you had have asked me this before I did further simulations, I would have said probably very heavily. However, it seems to be the case. So actually using your model and your constraints and also a more constrained LBA simulation, the results didn't really change as you add, this is where it gets a bit complex, right? As you add more factors, the constraint doesn't really help unless you constrain the least constrained condition. So for example, I gave a single factor, right, that you look at variation of. Let's say you add a second factor and you only allow drift rate to vary across that factor, right? That helps you better estimate drift rate across this factor, but it doesn't help you across this factor. Threshold estimation is still going to be just as noisy in the LBA. How do I put this? So if you're going to constrain the model, you've got to constrain that factor, the differences over that conditions. Adding extra conditions won't help except for if you're adding extra trials. It will obviously help you identify differences between in that factor, but not in this unconstrained factor. Does that make sense?
And it's not because you're attempting to allow all parameters to vary across all levels. Is that correct? That you're not making selective influence?
No. Oh, no. Oh, sorry. So yes and no. So if you allow all parameters to vary across the levels of one factor, then that will always have the issue. However, if you add a second factor to try and constrain things, that won't help you constrain this factor. You'll still get those issues there. However, if you start constraining this factor by saying, let's not estimate differences in mean drift rate. Let's not estimate differences in non-decision time. If you add those types of constraints, then yes, that will definitely help. But essentially, if you want better measurement properties for selective influence, then you have to constrain things on that level, on that factor, on those conditions.
Yep. Let me be a little bit more concrete in relation to a specific question, which is the eta, or the eta parameter in the diffusion model, which is often bagged as being difficult to identify. Now, if you look at how it enters into the predictions of the model, it accounts for the difference in the ordering of correct responses and errors. So the only circumstances in which you would expect to be able to identify that parameter is if you have a sufficient range of accuracy in which you get largish differences between correct responses and errors. So your ability to do that is actually going to be critically dependent on the range of difficulties that you embed in the design. So yeah, that's one very concrete instance where we can show that if you don't have a sufficient range of accuracy, you're not going to be able to estimate that parameter. So I think my question is, are there other versions of that kind of issue in which the nature of the design and the range of parameters that you've chosen will actually have an impact on your identifiability?
No problem. Okay, I see what you mean here. So the key thing here is that you're constraining eta to have the same value across these conditions, correct?
Yes. Yep.
Exactly. And so that constraint will save you, right? The key thing here is that if you were to allow eta to vary across these conditions, then you'd lose all that constraint, right? And you wouldn't be able to identify eta properly anymore. But it's the fact that you're constraining eta across these conditions that makes it identifiable. Okay. And yeah, so if you were to constrain threshold to have the same value across these two conditions, then it would be perfectly identifiable because you get rid of this trade-off with changes between conditions, right? But as soon as you start letting more and more things vary across these conditions, then the measurement properties deteriorate until you get essentially what you have in the Dutella et al. Study, which is just sloppy models estimating nothing of meaning.
Actually, and while I'm talking, one related question, you said that you could deal with the identifiability issue in models like the LBA by constraining the mean. What does that actually do to the model's ability to fit data? We looked at a similar problem in the fourth year models class in relation to the Poisson counter model, which has a similar sort of structure in as much as it's got two different accumulation rates. And there's a natural constraint, which is to say some of the rates are constant and allow the difference of the rates to vary. But that constraint, although it improves all sorts of properties, actually means the model fits the data much worse. So what happens to models like the LBA if you impose that constraint?
So this is an interesting question. I haven't fit a lot of data sets with it so far, so my conclusions are very tentative. Let me make that clear. But for me, qualitatively, it doesn't seem to make the fit too much worse. It makes the fit worse, but it's for me, it's not like the fit's getting terrible, right? You do see a decrease in fit, but you don't see what I'd call severe misfits, right? However, quantitatively, the fit definitely gets worse, right? Yeah. And in most cases,
you would be less concerned about quantitative fit, which you would expect, as to the sorts of qualitative properties in probability plots and things that we've regarded as being kind of key qualitative indicators of the performance.
Agreed, completely agreed. And in terms of the qualitative fit, for what I've looked at, it doesn't seem to get too horribly worse. It's not like this model is just fitting so bad that it's uninterpretable now. So it's you sacrifice a bit of fit, but not insane amounts, at least in my opinion, from what I've seen so far.
And finally, can you give I was a little puzzled at the apparently bad parameter recovery that you found with the Smith and Lilburn time varying diffusion model. And I guess I was puzzled by it because one of the things that we found was that there was really a high degree of consistency in parameter estimates across individual subjects when we fit it to data. So the slide that you showed was the performance of the growth rates of the individual subjects, the 20 individual subjects. And to me, it actually looks very, very regular and interpretable. there's not a large amount of individual differences, variation. And so, if it were the case that there were huge parameter trade-offs, I think as your parameter recovery study suggests that there might be, I would have thought it would have looked worse than that. So I'm a little bit puzzled why your parameter recovery study seemed to be doing so much worse than our reported fits.
So I'd be happy to talk about this more later, even later at some point. But I think the issue is you can still get, how do I put this? You can still get things grouped into one area, right? So for example, if I put fairly tight constraining priors on things, because I use Bayesian fitting, I could get everything within a reasonable area, right? I could, and the same if you're using a simplex algorithm that constrains the area is in or whatever you're using, right? I think it's quite easy to get things all within a reasonable area of values. I think the key, I think even then, everything kind of stayed within a range, right? It was within a rectangle or a square. Right?
So look, that's actually raising a really interesting big theoretical point, which obviously goes outside this conversation, which is the difference between kind of a theoretical model recovery, which is basically just saying, we simulate something and we try and recover the parameters, versus theoretically driven modeling. And so certainly that paper with Lilburn, was anything other than a theoretical. What it was really attempting to do was to put a set of constraints and a set of dynamics derived from the visual psychophysics literature into a model. And the thing that we thought was really exciting is that we recovered the same sort of time course. So that's a very different kind of enterprise, isn't it? And it's not just saying, we will rely on the model to tell us the ground truth, but rather we will attempt to come up with a larger theoretical story which unifies multiple paradigms.
So I completely agree here. There is, and this is something that I didn't get enough time to go into. I'm planning to write a paper on this, but it will take time till I finish everything. But the key is that the Smith and Lilburn paper, I'd like to say, was very good in that it built a very nice theoretical, constrained, time-varying drift rate model. Very nice. I very much liked it. The bit where it becomes an issue for me is when you start using that as a measurement model to, let's say, measure differences in drift rate across conditions. So I think the model itself is very good, and the model itself would be great to, for example, compare to regular diffusion models to see if there's time varying drift rates in the process, right? But I think the issue comes in that when you start using that in measurement context to say, well, does drift rate vary between conditions if you can't identify those drift rate differences? Does that make sense?
And I think it points to two quite sharply different scientific objectives. One is using models as measurement models, which is a very kind of applied question. So if I'm trying to distinguish population A and population B, I want to know if they have different boundary separations or drift rates. And I think that's very different from the question of the scientific ground truth of saying, what's the process that's applying here, in which case you would often, certainly as we did in the Smith and Lilburn paper, be looking outside the context of the particular model and the particular paradigm and be looking for a larger theoretical story which unified multiple paradigms. Sort of comment about the, about the different scientific objectives of measurement models.
I completely agree. And I think collapsing thresholds are still very interesting to compare, right? You just shouldn't use collapsing thresholds as measurement tools because they're a mess when it comes to measurement properties. So I agree. There's completely different objectives, and this talk was mostly focused on the measurement type objective that Heathcote and Ratcliffe and stuff often do.
And I think we did make the point in the Smith and Lilburn paper that collapsing boundaries and time-varying drift rates are non-identifiable. We summarised some simulations, you might remember, where we simulated models with time-varying drift rates and attempted to estimate the parameters using a model with fixed drift rates and time-varying boundaries, and they were repeatedly misidentified as time-varying boundaries, which is, I think, a version of your point.
Yes, totally. All right, cool. I'll send you more details when I have more details on this stuff, though.
Thank you.
Cool. So thanks very much, Nathan. That was awesome, and I think we'll generate a lot of food for thought for many of us. If you don't mind, I wouldn't mind just having a quick chat after this on a particular issue that I've got. So I think we should probably let other people go. So thanks again, and we might use our reactions to.
Everyone,
thank Nathan.
It's Simon's birthday, everyone. So please wish him a happy birthday.
Yeah, I thought we might skip that. But yeah.
All right. Thank you, everyone.
Thank you, Nathan.
See you later.
Thanks, Nathan.